Hello, welcome. In this video, we're going to practice priority scheduling, non-preemptive, priority scheduling, preemptive, and round robin. So let's get started. So let's just remember what the different calculations. CPU utilization is the percent of time the CPU is working. In these simple examples, we're always going to have 100% CPU utilization. That's because we're not having any events. All of our processes are just doing their CPU bursts. And that's just to get started, but we will have more complicated exercises where you have a process that does a CPU burst, then goes out to I/O, then has another CPU burst, and then you have another process that has a CPU, goes to I/O, does a CPU, goes to I/O, does a CPU. So this would make things more complicated, and because there's so much happening, you may not have 100% CPU utilization. But for these exercises where we're just getting started, we will be having 100% CPU utilization because all of our processes just do one CPU burst. That's not very practical in most systems. Processes don't just get admitted into the system and do a CPU burst. But in order to understand how these algorithms work, we want to start with simple examples. Throughput, throughput also is a difficult thing to measure with these simple examples because it's very obvious if we're given the process data, how many processes we're completing in an amount of time. But we could take a screenshot or a snapshot of a section of time and compare how many processes, say from time 20 to time 50, how many processes were able to get accomplished during that amount of time. But we are doing turnaround time. That's the time from admit until exit. Waiting time is the sum of periods in the ready state. And response time is the first part of the wait time. When it gets first from admit to the first time, from ready to the first time on the CPU. So let's get started with a priority algorithm. So let's take a look at this. We're going to assume that the arrival time of all these processes is time 0. So that means that all 5 processes have arrived at time 0. And let's just take a look. Now this is their CPU burst. So P1 has a 10, P2, 1, 2, 1, and 5. And this is their priority. So if you're doing a priority-based algorithm, we need to know which number is highest. And so priority 1 is the highest. So this one has a higher priority than all of the other ones, right? So this one right here, P2 has the highest priority. This is non-preemptive, which means that once the process gets on the CPU, it will not relinquish it until it completes its current CPU burst. So let's get started. Highest priority is P2. P2 will have the CPU for 1 time unit, and then P2 is done. So we could even say P2 waited 0 time units. Response time and the wait time is the same because there's no preemption, and the turnaround time is 1. Now at time 1, P2 is done. So now in our system we have P1, P3, and P4 and P5, and the next priority would be P5. P5 is going to get the CPU until time 6. P5 waited 1 time unit. It had to wait 1 time unit from when it arrived to get the CPU, and its turnaround time is 6 time units. Now the current time is 6. The next high priority is going to be P1. P1 will get the CPU for 10 time units. P1 had to wait 6 time units to get the CPU and has a turnaround time of 16 time units. Now we have P3. P3 has a CPU burst of 2 time units, so it will be on the CPU for 2 time units. It had to wait 16 time units to get the CPU and has a turnaround time of 18 time units. The reason that the wait time and the response time are the same is because they're only waiting 1 time. But later we will have exercises where you will see that the wait time and the response time will not be the same. All right, and then our last one to go is P4. P4 head to wait has a burst of 1, so it's done at time 19. And P4 head to wait 18 time units to get the CPU and finished in 19 time units. So now we can add up. If you add up your bursts, 10, 11, 12, 13, 14, 19, that matches. Our CPU utilization is 100% because the CPU is never left idle. And we can calculate these averages. I don't have a calculator in front of me to calculate these averages, but it's very simple. You just add these up and divide by 5 and add the wait time up and divide by 5, and then you can get those averages, and then you can use them to compare with different algorithms. So right now we're not doing any of the comparison. We're just understanding how to use a Gantt chart, how to read this data, and how to do these exercises. This is non-preemptive, so each process does not relinquish the CPU once it gets there. So here are the averages. The wait time is 8.2 average and the turnaround time is 12. And you could say, okay, I'm going to change this and I'm going to practice. I'm not going to give priorities. I'm going to do this same algorithm. I'm going to do shortest job first. So if you wanted to practice doing shortest job first, it would be you would start at time 0. So say they came in this order, so you would have P2 and P4. We would do P2 first, followed by P4, and then we have P3, and then we have P5, and then we have P1, and this would totally change the wait times, the turnaround times. Let's see what the wait times would be. So P1's wait time would become 9, and P1's turnaround time would become 19. P2's wait time would be 0, and P2's turnaround time would be 1. P3's wait time would be 2, and P3's turnaround time would be 4. And P4's wait time would be 1, and P4's turnaround time would be 2. And P5's wait time would be 4, and P5's turnaround time would be 9. So if you add 9, 10, 14, 15, 16 divided by 5, you can see it's a significantly reduced wait time. Now this is just an exercise. I'm just demonstrating for you the different ways in which you run these algorithms on these simple Gantt charts and make comparisons. All right, now we're going to do preemptive priority. So preemptive priority, you have to take into account the priority of the process. So P1, so 1 is the highest priority. And you also have to decide if the process has arrived or not, because if we just said preemptive priority, you don't get a good practice on the exercise unless processes are preempted, right? So if they all arrive at the same time, nothing's going to kick anything else off. So that's why we have staggered arrival times. Keep in mind that this is the CPU burst time, and these are the priorities. Okay, highest priority. P2 has the highest priority, followed by P2 has the highest priority, followed by P5, followed by P1, P3, and P4. However, at time 0, the only one that is in the ready queue at time 0 is P1. You have to take a look at the arrival time. P1 is ready to go, but then P1 has a CPU burst of 10, but P1 is not going to get to complete its CPU burst of 10 because at time 3, we have the arrival of P5. P5 is going to arrive at time 3. And when P5 arrives at time 3, P1 is going to be kicked off of the CPU because P5 has a higher priority, which is a 2, and P1 has a priority of 3. So what happens when P1 gets kicked off? P1 has 7 time units of CPU burst left because it was able to do 3 of its time units, and it's going to have a new arrival time of time 3. So now P5 is going to get on the CPU, but P5 has a priority of 2, and P2, which has a priority of 1, is going to arrive at time 4. So P2 with a priority of 1 is going to arrive at time 4, and P5 is going to be kicked off. When P5 gets kicked off, it's going to have 4 time units of CPU burst left, and it's going to have a new arrival time of 4. Now P2 is the highest priority, and nothing will kick P2 off, so P2 is going to get the CPU until time 5, and then P2 will be done. We can calculate P2's response time, wait time, and turnaround time. So P2 arrived at time 4, got the CPU at time 4, has a 0 response time. P2 also did not wait any extra time, so has a 0 wait time. And P2 has a 1 time unit of turnaround time, meaning all it did was it's 1 unit of CPU burst and then exited the system. Now the current time is 5. So the current time is 5, and in our ready queue, we have P5 is in our ready queue because it arrived at time 4. We have P1 in our ready queue, it arrived at time 3, and we have P3 in our ready queue that arrived at time 2. So even though the P3 has a earlier arrival time than the other ones, we have to look at the priority. So of the 3 processes that are in our ready queue, the one with the highest priority is going to be P5. So P5 will get on the CPU next. P5 has 4 time units of CPU bursts left, so P5 will be done at time 9, and now P5 is done. And we can calculate P5's response time, wait time, and turnaround time. P5's response time is 0 because P5 arrived at time 3 and got the CPU right away. But then P5 had to wait 1 time unit in order to let P2 do its 1 time unit of CPU burst. And P5's turnaround time is from the time it finished minus the arrival time. So you'd say the turnaround time is going to be 9 minus 3 because it arrived at time 3 and finished at time 9. And so the turnaround time is going to be 6. You could also add up the P5's wait time, which is 1, plus CPU time, which is 5, and that's going to equal the turnaround time. So now the current time is 9. All 3 of the remaining processes are in the ready queue at time 9. It doesn't matter the order in which they came if they're all there. P1 will go next because P1 is the highest priority, and P1 will go until time 16. P1 will be done. P1 response time is 0 because it got right away on the CPU. P1's turnaround time is 16 because it arrived at time 0 and finished at time 16. And P1 waited, P1 waited from 3 to 9, so P1's wait time is 6, which if you add up the wait time plus the burst time, it equals 16. So you can double check P1's wait time is 6 plus the CPU time is 10, which equals 16. So we're double checking P1's turnaround time. Now the next priority is P3. P3 has a CPU burst of 2. So P3 is going to have a response time. Well, P3 arrived at time 2 and had to wait until time 16 to get the CPU. So the response time for P3 is 14. P3 did not have to wait again, so it only waited once, so it's 14. P3 finished at 18, and so the turnaround time is going to be 16. You can double check that by doing P3's wait time is 14 plus the CPU time is 2 equals 16. So the total time that P3 was active in the system is 16 time units. Then our last process to go, lowest priority, is P4. P4 has a CPU burst of 1 time unit. To double check this, you can add up the CPU burst, 10, 15, 16, 19. So that checks. We have 100% CPU utilization. And to get P4's wait time, P4 arrived at time 6 and waited 12 time units, which is also the response time. And the turnaround time is going to be 13, which adds up because P4 has only a 1 time unit of CPU burst. So if you take P4's wait time, which is 12, plus CPU time, which is 1, that equals 13. So to get the averages, you would just add this up and divide it by 5, add the response time, divide it by 5, and add the turnaround time and divide by 5. All right, so the next one we're going to do is going to be round robin. So round robin is a CPU scheduling algorithm. It's first come, first serve, only that should say process. Huh, that's funny. Okay, it has a time quantum. So it's first come, first serve. So to make it easy, they all arrive at time 0. But what happens is each process only gets 4 time units on the CPU. So it's going to have 4 time units on the CPU, and it's going to then be interrupted and let the next one go. So we're going to assume that they arrive in this order, P1, P2, P3. So let's get started with this exercise. So P1, we have current time is 0. P1 is going to get 4 time units on the CPU. It's going to go until time 4. I'll use blue for P1 and I'll use purple for P2 and I will use green for P3. So P1 will be blue, just to remind me. P2 will be purple and P3 will be green. So P1 is going to get on the CPU for 4 time units. So it's going to have a new arrival time of 4 and it's going to have 20 time units left of its CPU burst. Now we have P2. P2 is going to get 4 time units on the CPU. It's going to have 1 time unit left of its CPU burst, and it's going to have a new arrival time of 8. Now, since we're doing first come, first serve and round robin, it's not a big deal about the arrival time, but there are combination algorithms, multi-level feedback queue priority with round robin, and that can become complicated. So I'm just trying to get you used to using everything and keeping track of everything so that when it gets more complicated, you have already been practicing by keeping track of the arrival times and all of that. All right, so our next one is P3. P3 is going to get the CPU until time 12. So it's used up 4 time units of its CPU burst and has a new arrival time of 12. Now we're just going to cycle through again. We have P1. P1 is going to get back on the CPU until time 16. So it's going to have 16 time units of its CPU burst left. And a new arrival time of 16. Now we have P2. P2, it has only 1 CPU burst. I don't know why I did that. It didn't have, I've already made an error, so that should be 5, right? So when P2 went here, it did not use 8 of a CPU burst, it used only 4. So those of you paying attention, I have fixed it now. So it has 5 left of its CPU burst. So now it will go till time 20, and now it will have 1 left of its CPU burst. And then we will have P3. That will go until time 24. Oh, P2 has a new arrival time of 20. Now we have P3 that goes until time 24. So it has 9 time units left of its CPU burst, new arrival time of 24. Again, I know that we're doing round robin, so these new arrival times are not that big a deal, but I just want you to get in the habit of practicing that. All right, so now our next one is going to be P1. Oops, wrong color for P1 is blue. P1 has 16 time units left, so we'll go to 28. Now has 12 left. New arrival time of 28. Now we do P2, which is going to be done now. P2 is finished at time 29, and P2 is done. So now we could do our calculations for P2. P2's response time. I'm going to move the response time over here because I ran out of space. The response time for P2, well, P2 arrived at time 0, first got on the CPU at time 4, so P2's response time is 4. P2's wait time, well, P2 had to wait 4 time units plus, oops, 4 times, I need more space here. Let's do the response time here. For P2 is 4 and the wait time, so we can add it up. So 4 is the first measure. So P2 waited and then got there at time 8 and had to wait until 16, so had to wait 8 more time units. And then got there at time 20 and had to wait till 28, so waited 8 more time units. So P2's wait time is going to be 16. Is that correct? P2 waited 4 time units here, then waited from 8 to 16, which is 8. Oops. And then waited from 20 to 28, which is 8. So that's 16, which equals 20. So that's going to be P2's wait time. P2's turnaround time is 29. You can double check P2's turnaround by adding up the total wait time plus the CPU, which is 9. And so the turnaround time is going to be 29. All right, so now we only have to round robin between P1 and P3. So the next one to go is going to be P3. Because we remember here that P3 arrived at 24 and P1 arrived at 28, so the next one to go would be P3. P3 gets the CPU for 4 time units until time 33, so it's going to have 5 left and a new arrival time of 33. Now we have P1, which is going to go until time 37. So it's going to have 8 time units left, 37. Then we have P3 until 41, has 1 time unit left, 41. Then we have P1, which goes until 45, has 4 time units left. Then we have P3, which has only 1 time unit left, so it goes to 46. And then we have P1, that goes until time 50. So you can we have 100% utilization. To double check, you can add up the CPU bursts. 24 and 9 is 33 and 17 is 50. So we add up the CPU bursts, so we haven't made an error there. Once you get your Gantt chart right, you can actually do all the calculations right from your Gantt chart, or you can look at the numbers that you wrote. So let's do our calculations. P1 arrived at time 0, so P1's response time is going to be 0. P1 turnaround time arrived at time 0 and finished at time 50. P3's response time will be 8. P3 had to wait 8 time units to get the CPU, and P3's turnaround time is 46. Now you could, to get the wait time, you could take the turnaround time and subtract the CPU time, and that would give you the wait time in this case. So I could say for P1, 50 minus the CPU time, which is 24, equals 26. So the wait time for P1 should be 26. But let's double check P1's wait time. So P1 waited here 8 time units, right? It waited right here 8 time units. Then it waited here from here. It waited another 8 time units. And then it waited here from 28 to 33, which is 5 time units. And then it waited 4 time units. And then it waited 1 time unit. So if you add that up, 16, 20, 25, 26, then you get 26 for the wait time. So that is accurate. So I just want to make sure you understand where these numbers are coming from. P3, you can take P3's turnaround time, which is 46, and subtract the CPU time, which is 17, and that should give you a wait time of 29. But to calculate P3's wait time, we can also look at our chart and get all of the times that P3 waited. So first you have the response time, which is 8. And then P3 had to wait from 12 to 20, so 8 more time units. Then waited from 24 to 29, which is 5. Then waited from 33 to 37, which is 4. Then waited from 41 to 45, which is 4. So if you add that up, 16, 20, 25, 29, then you get the 29, and that is accurate. So here is how round robin works. I recommend that you practice these simple algorithms, because when we get to multi-level queue and multi-level feedback queue and processes that have CPU I/O, CPU I/O, it becomes a lot more complicated. So understanding just these basic algorithms is very helpful.